Now let's go ahead and talk about the point estimation first. It is usually population mean estimation is required here. For example, average cumulative grades of ISTEC graduates, for example, or durability of a new type of steel, or the number of deaths per year at a given location, etc. The idea is, you can have different estimators, of course, okay, different bows for shooting an arrow, for example. For population mean, you can have mode, median, sample arithmetic mean, etc. You can have many different estimators for this purpose, but we usually rely on arithmetic mean because it has the least variance and it is always unbiased. We just recently discussed that having an estimator with unbiased and least variance is very important, right? And arithmetic mean is useful in that sense. Okay. So, three main conclusions can be drawn from a population with given mean and variance right here. Now, let's try to address them one by one. Okay, when we have a population with mu and sigma square, okay, mean and variance, we have a population like this. The first one is the estimator, arithmetic mean, is a good estimator of mu. This is the first one, the first conclusion that we can draw. The second one is standard deviation of arithmetic mean is gives us information about the precision of the mean. In fact, so it is represented with this one, like this formula. Okay, we're not proving anything here, but let me write them just to give you an idea. Here, the n correspond to the number of members in the population, and this small n corresponds to number of members in the sample set. Considering that capital N is usually much larger than, considering that capital N is usually much larger than the small n, it can be easily rounded to 1. This part can be easily rounded to 1. Why? Because it's, infinity minus n over infinity minus 1 or something like this, okay? You can reduce it to 1. That's the idea. So this one will go ahead, disappear, and you will be left with only this one. This is another conclusion that can be drawn. And the third one is if your n is large enough, x can be said that it shows normal distribution. Arithmetic mean shows normal distribution. This is also another conclusion that can be drawn. That means x hat is an unbiased estimator for mu. That's the idea. So whenever your n increases, samples increase, your variance or standard deviation will decrease. And you should keep in mind that, you can read this from the book as well, central limit theory states that given certain conditions, the mean of a sufficiently large number of independent random variables will be approximately normally distributed. So this is what we're grounding our approach right here. All right, let's try to explain this with an example together. Suppose that you have a six-sided die. six-sided die like this, and your population mean would be your expected value. Let me write it like this, right? And that would be 1 over 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? And that would be 3.5. All right. If we take 5 samples, if we throw the die 5 times, does that mean a good estimator for population mean? 5 times. If we roll the die 5 times, is it a good estimator for population mean? In other words, or such that, how far are we expecting the mean fall from mu? Our mean should be around mu, but how far? Usually, regarding such type of questions, Chebyshev theorem is used. Chebyshev, I hope I pronounced it correctly. What does Chebyshev theorem tells us is random observation from population, where we have random observation from our population X. You can have mu minus plus a sigma for far from. Mu probability can be represented with 1 minus a square. I mean, how many standard deviation you deviate from the population mean here, where your a is equal to or larger than 1. So Chebyshev theorem states that probability of falling within this range, a sigma, this is your sample average, mu plus a sigma, that should be at least this probability here. If you put here, and the standard error is, of course, calculated like this again. So for 2, for example, if you put here 2, for example, you can say that for mu minus plus 2 sigma x, this one is what you're calculating from the samples here. It is for 1, 2 square here. This is the probability. At least 75% of arithmetic means will fall within this range, from mu. So this is called, also it has another name which is called, popular name, this is called the error range. Okay, this is another population jargon for this. So if your x shows normal distribution, there is also another thing that your mu can fall in this range, and this will cover 95% of all sample means here. And many people practically take this one too as well. But this is called the empirical rule. Empirical rule in this sense. You see, it's a bit different than Chebyshev theorem because it assumes that the distribution is normal. But okay, maybe Chebyshev theorem is a bit less brave in this sense, but you should keep in mind that Chebyshev theorem can be fit into distributions other than, can be useful for distributions other than normal distribution as well. Okay, like your distribution should be like this all the time to conclude like this. But suppose that your distribution is like this, or your distribution is like this, or like maybe you can have many different types or something like this. Again, you can use Chebyshev theorem in this sense. That's the difference between two approaches, I guess. Okay, if we go back to our example again, our sigma square will be expected value of x minus mu square 1/6, 1 minus 3.5 square plus, you know this from chapter 1, right? How to calculate the standard variance here, plus up to 6 minus 3.5 square here. And when you make the necessary calculations with your calculator, you will end up with 2.92. Okay, and this is your variance, and your sigma will be square root of this value. It will be 1 minus 1.71, and 2 sigma will be 2 times 1.71 over, here you have how many samples? 5 samples, right? And in your 5 samples, this one will be 1.53. So you can conclude that like minus plus 153 away from population mean is at least 75% of the measurements will fall like 1.53 plus minus range from mu. That's it. So let's consider another example here, our last example about the point estimation here. Suppose that, again, this example is taken from the textbook as well, like daily production at a chemical factory, daily production at a chemical factory, like and 50 days samples are taken, like you take samples for 50 days, and their averages are this one with a standard deviation of 21. This is for daily samples, for daily samples. So we're trying to estimate mu here. We're trying to estimate mu here. This is a bit different from our six-sided die example, because there we had the mu in fact. But here we don't have the mu. We're trying to estimate the mu, some unknown variable here. And our 2 sigma x would be 2 sigma over this one. This is our formula. However, we don't have this one. This is rather tricky. But if you don't have it, you can go ahead and use it from samples. That's it, because that's all you have. You don't have the real population value here. And you go ahead and use your calculator here, and you will have this difference. So your mu is located for x, since your x is kilograms. Oops, I forgot. This is for kilograms production. I forgot. So it is valid for this range. Okay, minus plus 5.94 range. Like if you use Chebyshev theorem here, your at least 75% of your mu will fall within that range, which is unknown, but 75% of them, the predictions will fall with mu can be right between these values. Okay, it is valid for this given range. That's the idea about point estimation for the population mean.